Dear student, today we shall begin a chapter force and pressure. We have already discussed two parts of this lesson. Now we will discuss the new part in this chapter. So the first topic of this lesson or of this session is atmospheric pressure. Now let's see what is the atmospheric pressure. So students, air surrounds the earth from all sides, and this layer of air is called as atmosphere. The atmosphere exists to about 16 kilometer height. It further extends up to about 400 kilometer in a very dilute form. So students, you can see the different layers of the atmosphere. The pressure created due to the air is called the atmospheric pressure. Imagine that a very long hollow cylinder of unit cross-sectional area is standing on the surface of the earth and it contains air. You can see a hollow cylinder containing air molecules within it. Weight of this air is the force applied in the direction of the center of the earth. This means that atmospheric pressure is the ratio of this weight divided by the area of the surfaces. The air pressure at the sea level is called 1 atmosphere pressure. Now air pressure decreases as one goes up in height from the sea level. Now students, you can see in the picture, look at all the atoms pressing. You can see a cylinder, an object which containing the air molecule. So at the sea level the pressure is very higher, but as we go above the sea level the pressure decreases. So as height increases or altitude increases, the pressure goes on decreasing. Now students, 1 atmosphere is equal to 101 into 10 raised to 3 Pascal which is equals to 1 bar, that is equal to 10 raised to 3 millibar, and 1 millibar is equivalent to 10 raised to 2 Pascal, or that is hectopascal. Atmospheric pressure is specified in the units millibar or hectopascal. The atmospheric pressure at a point in air is equal from all the sides. Now students, how is this pressure created? If air exists in a closed container, the air molecules in random motion continuously hit the walls of the container, that you can see in the picture also, and in this interaction a force is exerted on the walls of the container and pressure is created due to that force only. We constantly bear the atmospheric pressure on our. Now students, however, the cavities in our body are also filled with air and arteries and veins are filled with blood. Therefore, we do not get crushed underwater, and due to atmospheric pressure, as the pressure is balanced, pressure of the body is balanced. The Earth's atmospheric pressure height from the sea level as shown in the picture that I also told you just now. Okay, use your brain power. At the sea level, the atmospheric pressure 101 into 10 raised to 3 Pascal is acting on a tabletop of size 1 meter square. Now under such a heavy pressure, why doesn't the tabletop crumble down? Now student, this is because there is air below the table as well. Students, the pressure of air below and above the table are same. So the force exerted by the air above the table is countered by the force exerted by the air below the table. That's why the tabletop doesn't crumble down. Next topic in this session is buoyant force. Now let's see what it is. Now to understand this type of force, let's do one activity. Students, take a plastic bottle and fix the lid very tightly. Now place it in water and see. It will float on water. Try and push it into the water. Even when pushed, it continues to float. This experiment can also be done with a plastic hollow ball. Now fill the bottle with water to the fullest capacity and close the lid and release it into water. The bottle will float inside the water. Why does this happen? So students, the empty plastic bottle floats on the surface of water. On the contrary, the bottle full of water floats inside water but does not go to the bottom. The weight of the empty bottle is negligible as compared with the weight of the water inside. Such a bottle with water neither floats on the surface nor does it go to the bottom. This means the force due to gravity acting downwards must have been balanced by an opposing force in the upward direction on the bottle filled with water. And this force must have originated from the water surrounding the bottle. Now let's see the definition of buoyant force. The upward force acting on the object in water or other fluid or gas is called as buoyant force. Now students, this is an upward force exerted by the fluids, that is water, that opposes the weight of a partially or fully immersed object. And buoyant force is greater than the gravitational force in causing object float into the fluid on the surface. Here I have put one picture for you. See, you can see an object that is float and sink. Now upward arrow, that is the upward arrow indicating the gravitational force, and the downward arrow inside the fluid is indicating the buoyant force. Okay students, now let's answer some questions. While pulling a bucket from a well, the bucket full of water immersed fully in water appears to weigh less than when it has been pulled out of water. Why? Students, this is because of the buoyant force which acts against the gravity pull of the earth make a bucket weightless. And always remember, the buoyant force is always greater than the gravitational force. Now next, take a piece of thin aluminium sheet and dip it in water in a bucket. What do you observe? Now shape the same piece of aluminium into a small board and place it on the surface of water. It floats, isn't it? So students, it will sink. Why? Because the density of water is less than the density of aluminium sheet of it. And what is density? It is a mass per unit volume. Now next question is, an iron nail sinks in water, but why does the massive steel shape float on it? You can see a picture of nail which is immersing into the water and the board which is floating on the surface. So when an object is dipped in a liquid, a buoyant force acts on it and hence it appears that the weight of the object is reduced. Why this is so? So students, the weight of the water displaced by the ship is equal to its weight, so it will be float into the sea. Whereas the weight of the water displaced by the iron nail is less than its weight of the water, so the iron nail will sink into the liquid. Now students, it becomes easier to swim in seawater than in fresh water. Why? This is because the density of seawater is higher than the density of a fresh water, and due to salt dissolves in seawater. Again I am explaining you, density is the mass per unit volume. Now students, buoyant force depends on the two factor. Now let's see the factor. volume of the object, the buoyant force is more if the volume of the tipping object is more. And second is density of the liquid. So more the density of liquid, more is the force of buoyancy. So this depends on two factors, which are the volume of the object and density of the. Now let's see the next topic in this session, that is Archimedes Principle. Now students, let's do one of the activity. Take a long rubber band and cut it at one point. At one of its end, tie a clean washed stone or a 50-gram weight as shown in the figure. You can see figure. Now hold the other end of the rubber band and make a mark there. Keep the stone hanging in air and measure the length of the rubber band from the stone to the mark made earlier. Now we have to take water in a pot and hold the rubber band at such a height that the stone will sink in it. Again, measure the length of the rubber band up to the mark. What is observed by this? This length is shorter than the earlier length. Okay. Now, while dipping the stone in water, length of the stretched rubber gets slowly reduced and is minimum when it sinks completely. What could be the reason for a shorter length of the rubber band in water? Now students, when the stone is sunk in water, a buoyant force acts on it in the upward direction and the weight of the stone acts downward. Therefore, the force which acts on it in the downward direction is effectively reduced. How much is the magnitude of the buoyant force? Is it the same for all the liquids? The answer to this question are embodied in Archimedes Principle. Now students, this principle states that when an object is partially or fully immersed in a fluid, a force of buoyancy acts on it in the upward direction, and this force is equal to the weight of the fluid displaced by the object. So student, this is the Archimedes Principle. Now let's see the introduction to the scientist. Students, Archimedes was a Greek scientist and a mathematician with sharp intelligence. He found out the value of pi by numerical calculation. His knowledge of levers, pulleys, wheels in physics was useful to the Greek army in fighting against the Roman army. He became famous due to his work in geometry and mechanics. When he entered a bathtub for taking bath, he discovered the above principle by observing the overflowing of water. He came out in the same state, shouting, "Eureka, Eureka," meaning "I found it, I found it." The use of Archimedes principle is very wide. This principle has been used in the construction of ships and submarines. The instruments such as lactometer, hygrometer are based on this principle only. Now students, let's see some formula. Density of substance and relative density. Now the formula for the density is equals to mass upon volume. The SI unit, so the density is mass per unit volume, and the SI unit for density is kilogram per meter cube, and the property density is very useful in deciding the purity of the substance. The relative density of a substance is expressed with respect to density of the water, and relative density will be equal to density of substance upon density of the water, and this being a ratio of two equal physical quantities, it has no unit. Relative density of a substance is called its specific gravity. So students, I hope this will help you, and this is all about this lecture. Thank you students.